Do you see the screen sharing? And
Yes,
is it okay?
oh, that's great. Excellent.
Okay. Let me start.
Yes, please.
Okay. Hello, my name is Oleg Bakhteev. Today I will talk about Bayesian selection of deep learning model structure. We consider the problem of deep learning model structure selection. The main task is to propose some criteria of optimal and suboptimal complexity of the model, as well as a method for model selection. One of the main problems with deep learning models is their implicit complexity. As an example, this slide shows two plots for the autoencoder model. The graph on the left shows that by removing uninformative and irrelevant parameters, you can achieve a slight decrease in quality with significant decrease in the number of parameters. The plot on the right shows that a model with less parameters may be more robust to noise in the dataset. Here we add some Gaussian noise to the samples from the dataset and evaluate its accuracy. In general, deep learning models are often parameterized, which leads to poor robustness and high computational costs. The correct choice of the model and model structure leads to both reduction in operating costs and an increase in the performance of the final model. A model is a differential function from an object feature space to the space of labels. The model consists of set of superpositions. This set and the relationship between them is determined by the structure of the model. We can notice that in terms of this definition, a deep learning model is a well-studied object, and there is a number of approaches that were already proposed to select such models. For example, the Akaike criterion or the Schwarz informational criterion. In practice, these criteria are not straightforwardly applicable because of the excessive number of parameters in the models, which lead to an excessive penalty for deep learning models. We propose to select a model with respect to its complexity. This concept can also be defined in different ways. Here are two examples of naive approaches to define it: number of parameters or number of superpositions in the model. For a complexity assignment, we propose to consider a deep learning model as a probabilistic model. Introduce some probabilistic assumptions about the distribution of parameters. These assumptions are characterized by prior distribution over the parameters and the structure of the model. By hyperparameters, we call the parameters of the prior distribution. For simplicity, we concatenate the parameters by groups. The concatenation of all gamma vectors, the vectors that control the superposition of submodels in deep learning model, is called by the structure of the model. The match parameters are the parameters of the optimization problem, and their values are assigned expertly and not optimized. Optimization function for deep learning model often consists of likelihood and regularization terms. There are two types of likelihood terms presented here for classification problem and for regression one. Note that for the regression, we can introduce an additional matrix B, which is responsible for the covariance of the model errors. This covariance is included in the hyperparameter list H. We consider the Gaussian distribution with zero mean as the prior distribution. The covariance matrix A will also be a hyperparameter of the model. The prior distribution acts as a regularization penalty, and it's responsible for the correspondence of the model parameters to our assumption about the distribution of parameters. Note that this term is very close to the usual L2 regularization, and so we can also introduce a distribution on the model structure which is responsible for the superposition of submodels in our model. This will be discussed later. Let's consider a simple example, a single layer neural network. The task is to choose a structure of such a network. For this very simple case, this means to select a number of neurons in the hidden layer. Let the choice be made between three alternatives with different number of neurons. Of course, we can represent them as models with absolutely the same structure, just using the following expression, which is presented on the bottom of the slide. Where all the matrices of parameters have some predefined zero elements. So each matrix of hidden layer will have 3 rows and 3 columns, but some of the columns need to be 0. Then the hidden layer will have the dimension equal to 3, but some of its component will be 0 for the for the central and right models displayed on this slide. There we consider a more formal problem description. Let the choice be made between two alternatives, two hidden layer numbers. Each alternative is specified by a generalized linear function with its own matrix. Each matrix has a predefined number of non-zero columns. This number of non-zero columns determines the number of neurons on the hidden layer. Thus, the task of choosing a model is reduced to choose one of two alternatives. The vector defining the importance of each alternative and the model for the model will be called the structure of our model. So if the vector gamma, which corresponds to the structure, is strictly binary, we get only one of the submodels into the model. And so we reduce our problem to the discrete optimization problem. Many modern algorithms for choosing for neural architecture selection work according to this principle. The model is represented as a graph where the edges correspond to the to nonlinear operations, and the vertices correspond to the intermediate results of these nonlinear operations. Of course, this approach basically works not on some simple networks like in the previous examples, but on more complex models that include convolutions, pooling operations, recurrent models, and so on. For this example, a similar method can be used. Again, we represent the model as a graph with different alternatives. Here we choose between convolution and pooling operation. We can set a multiplier in front of each term for each alternative. And if the vector gamma for these multipliers is binary, we get a discrete structure. Note that the pooling operation has no parameters, so not all the submodels in the superposition have parameters at all. Here is a formal definition for our model considered as a graph. There is an acyclic graph. The vertices of the graph will be intermediate states of our data set, and the edges will be the basic primitive functions for them. The graph with the set of given functions will be called a parametric family. Illustrate the main types of constraints that can be introduced on the structural parameters of gamma. The top left figure shows the case when the structural parameter gamma belongs to a Boolean cup. So each gamma component belongs to a binary set of values. The lower graph corresponds to a more interesting case. Here the gamma belongs to the set of vertices of the simplex. In the context of the previous example about a neural network with one convolution operation and one pooling operation, these constraints allow us to choose strictly one alternative and solve the problem of the model selection for this neural network. Since it's rather difficult to solve the tasks of structure selection straightforwardly, we can make a relaxation. then the structure vectors gamma will be not binary, and these forms of the relaxations are shown in the right part of the slide. We propose to use the Gumbel softmax distribution as a prior distribution for the model structure. Its form with different prior distribution parameters, hyperparameters, is shown at the top of the slide. The distribution is set on the simplex and depends on two parameters, temperature and concentration. The concentration is a vector that defines the contribution of each vertex of the simplex to the final distribution. The temperature specifies how much concentration will be near the vertices of the simplex or in the center. The Dirichlet distribution has similar characteristics, and it is shown that this distribution is highly unstable when using gradient optimization methods. Therefore, we prefer to use Gumbel softmax. So here is a brief overview of our probabilistic model. We use a model with prior on parameters and the structure. The model's hyperparameters are covariance matrix A and the concentration parameter of the Gumbel softmax distribution. The temperature parameter is a meta parameter. It it controls how close our optimization would be to the discrete one. And the less the temperature we have, the closer our optimization will be to the discrete optimization. However, if the optimization is too close to the discrete one, it would be hard to optimize our problem. We select model according to the minimum description length principle. This principle states that we should choose the model whose description length plus the description of the data set given the model is minimal. The MDL principle, minimum description length, not a ready solution. And one of the interpretations of this principle is included into Bayesian approach. The Bayesian interpretation of this principle is the evidence of the model, the integral of the likelihood of the data set over all possible values of the parameters with respect to its prior. So here is an illustration of the evidence. The left plot shows three models, the simple one, the complex one, and an optimal one. The y-axis is the likelihood, and the x-axis corresponds to some different data sets from the general population. The simple model's likelihood is rather stable across all the data sets, but its value is low. The complex model's likelihood is much higher, but it's shaped as a sharp peak near one point on the x-axis, and therefore it is impractical to use it if we use it for prediction tasks. The optimal model is a trade-off between these two models, the simple one and the complex one. The right plot is an example of the evidence behavior. The dataset was generated by second order polynomial, and here are three models: linear, second order, and fifth order. We can see that the second order and fifth order models describe the dataset perfectly, but the evidence integral for the fifth order model is low because it's too complex. Therefore, we can say that the evidence allows us to select an optimal model that controls the balance between likelihood and the model complexity. The main challenge with Bayesian model selection is that the evidence integral is analytically intractable. To estimate it, we use evidence lower bound. The method is false, introduce some distribution Q, approximating the unknown posterior distribution of parameters. Then the lower bound for the logarithm of the evidence integral can be obtained using Jensen inequality. The problem of finding the value of the evidence integral bound is reduced to the problem of finding the optimal values of this distribution Q. In practice, some parametric distributions are considered as variational distribution Q, but we also can consider more interesting distributions. For example, if we consider gradient descent step as an operator that transfers the parameter distribution, then the empirical distribution of the optimized parameters can also be used for the evidence lower bound estimation. The gradient descent itself doesn't optimize evidence. Therefore, starting from some iteration number of the optimization will decrease the evidence lower bound, which indicates the beginning of the overfitting. Thus, as a variational distribution of parameters, one can take not some parametric distribution, but also simply optimize the parameters of the in the standard procedure. At the same time, it's possible to get an estimate of the start of overfitting without using cross-validation. Let's move to the formal problem statement. Given a variational distribution approximating the posterior distribution of the model parameters, given two functions, a validation loss function and a train loss function. The train loss function is responsible for optimizing the parameters, and the validation loss function is responsible for optimizing the model's hyperparameters. The problem of model selection is a two-level optimization problem, which is displayed on the slide. At the first level, at the top level, we optimize the model hyperparameters, while the variational parameters of the model are optimized at the second level. The optimal variational parameters are implicitly depend on the hyperparameter values. We propose the following optimization problem. This problem contains two levels of optimization. Each of the level contains 2 or 3 terms. The term for the likelihood for the prior distribution and the term for the structure regularization. Generally, we can also include the last term into the structure prior. The proposed method generalize different optimization problems, including maximum likelihood and evidence lower bound optimization, model complexity increase or decrease. We can also perform some optimization procedure similar to exhaustive structure search using structure regularization. At the right part of the slide, we can see different structures obtained using optimization with different regularization terms. As we can see, the regularization can lead to different structure selection strategies. For the B-level optimization, there are several methods of optimization. Here's a simple example. There is a data set and a polynomial regression problem for it. The order of polynomials is 10, so the naive approach to fit the regression leads to high overfitting. Optimizing prior distribution parameters, we can get a more acceptable results, which is close to the linear one. On the left slide, on the left part of the slide, there is an optimization for the evidence lower bound optimization, and on the right part, there is an optimization using cross-validation procedure. Since the data set we used is extremely small, the cross-validation procedure doesn't allow us to optimize hyperparameters correctly. So the variational approach is preferable for this case. A more interesting case, the neural network hyperparameter optimization for the classification problem. The dataset is Wisdom, which contains records from the accelerometer. And again, the left plot is for the variational approach, and the right one is for the cross-validation. There we compare 4 methods, including random search, DRMAT, and HAWK methods that use an approximation of the optimization problem. These 2 methods, DRMAT and HAWK, require to make a gradient step for the hyperparameters only once in an epoch. So it's rather slow. The greedy method uses a local approximation to the hyperparameter gradient step. And as we can see, for the rather large data sets and complex models, it's quite preferable. So let's go to the structure analysis. Consider a simple data set for some toy example. A data set was generated from the Gaussian distribution. We again consider three alternative models: an optimal one, a complex model that tends to overfit, and a constant, a simple model that has a very poor predictive performance. Now we select the model using a relaxation procedure with Gumbel softmax distribution. We have a parameter of the temperature for the prior distribution that controls how the optimization will be similar to the discrete one. And also we have some meta parameters that control the balance between the likelihood and regularization. So on this slide, we see the structures we obtained from this experiment. We can see that for very low temperature, we see that for very low temperature, the structure is concentrated on the vertices of our simplex. Our simplex represent our structure, and so the model works in interpretable way. When the temperature is very low, the model optimization problem is similar to the discrete one. For the temperature rather high, we see that the model structure is concentrated in the center. So the higher we get a temperature, the more concentration of our structure probability mass concentrated in the center of the simplex. Here are the plots for the prediction performance. We can see that the temperature poorly controls the predictive performance, but the balance between the likelihood and the prior can influence it. For example, if we have prior very small in comparison to likelihood term, we see that the model tends to overfit, and it's rather okay for this balance. So if we wonder what's the role of our prior distribution, we can see the interpretation of its role on this slide. Here is an example from our article, which is in progress, hypernetworks for deep model complexity control. There is an example for the dataset Cypher 10. There are three neural networks, convolutional neural networks that were trained with different prior term. So if we have a rather small prior term, the blue one, for example, we can see that the model has a very high accuracy, but it's rather it's not very robust to some pruning procedure. On the x-axis, we can see the number of the percent of parameters to be pruned from the convolutional neural networks. If the prior term is rather high, we can see that the model has a rather poor accuracy, but it's more robust. If we continue to analyze the structure, we wonder about two questions. Can we control the model complexity at the inference step, not at the training step? And can we select some robust architecture, and what properties should it have? For the model complexity control, we propose to use hypernetworks. A hypernetwork is a mapping from a set of variables responsible for the properties of a desired model to a set of its parameters. So we can use hypernetworks to model the dependence of the model parameters on the its desired complexity. For this procedure, we consider a generalized evidence lower bound function, which is displayed here. We can see that it's quite different from the usual evidence lower bound. We can see a lambda term, a lambda multiplier, which controls the importance of the prior in our optimization procedure. And if we use hypernetworks to model parameters of deep learning model, we can optimize not only one model, but a continuous set of models in one procedure. So there are some plots from our work. Here we see that on the left side there is a plot of accuracy and pruned parameters percent, and on the right side we can see the same plot, but with hypernetwork usage. As we can see, hypernetworks rather accurately model these dependence, and therefore we can use them to model the complexity of the deep learning models. If we continue our work about hypernetworks, we can go further and try to model not only the parameters of the model, but also a structure of the model with respect to complexity control. Here we use as a baseline DARTS method. It's a gradient method that is used for neural architecture search. Its main principle is on the slide. We use, as in the formal problem statement, we use some gamma vector that controls the importance of all the operations, and we use softmax function to normalize it. So for the DARTS method, we use B-level optimization with the optimization of structural parameters on the top level and the parameters on the second level. Our proposal is to use not a constant vector of gamma, but a mapping from from the model complexity to some vectors of the structure. And here is a plot for fashion minis data set. There is a comparison of DARTS method and our proposed method. The DARTS method has only one point because it doesn't control the complexity, and our proposed method controls the complexity. So there are some lines for different runs of the experiment. As we can see, we can control the complexity rather good, rather accurately. If we lower the complexity, we get the simpler model, but the accuracy also decreases. And here are some cells for this method that we can obtain using different complexity of the model. On the left slide, there is a cell for very simple model. We obtained it practically doesn't contain any convolutional operations, only pooling ones. And for the complex CNN cell architecture, there are many convolutional operations. So it's more complex, but it's more accurate. So using hypernetworks for the model complexity control, we can obtain different structures for deep learning models. And for the robust architecture, there are some experiments. We analyzed robustness in different ways. First of all, we analyzed robustness to noise in data. We considered two experiments with random noise and with adversarial attacks. And for the robustness to model modification, we also considered two regimes, parameter modification and structure modification. For the noise in the dataset, we considered the following experiment. We used MNIST dataset and tried to optimize our hyperparameters to maximize the evidence lower bound. As we can see, different algorithms obtain different quality and moreover, different robustness to the noise in this data. So we can conclude that correct hyperparameter optimization leads to the model robustness under the noise. And for the adversarial attacks, we used DARTS method with some different modifications. We used FGSM method. It's a somehow baseline for gradient attacks for this experiment, and evaluated how our model should work with different FGSM attacks. Here are four plots, darts with using Gumbel softmax instead of softmax, and two darts runs with variational gamma, variational structure, and variational structure and parameters. As we can see, including Gumbel softmax into our optimization procedure leads to more robust architectures under some adversarial attacks. And if we use variational optimization, it also gives some increase in robustness. So for the structure pruning, we randomly pruned some edges from our model. And as we can see, if we use Gumbel softmax instead of softmax, or we use variational approach, we also obtain more robust architectures than the naive DARTS one. So this leads me to the end of my presentation. If you have any questions, I would be glad to answer them. Thank you.
Oleg, thank you very much. So, dear friends, if you would like to say something. Otherwise, just go to the slide number 11. In fact, we must keep it simple. Yes.
Mm-hmm.
So, first of all, how these vertices, black dots, say,
Mm-hmm.
Are connected to the distribution. I mean, yes, directly distribution or
mm-hmm.
What kind of?
So for both the Gumbel softmax or the directly distribution, we use a distribution that is defined on the simplex. So it's defined on, we can say that it's defined on the set that is displayed on the bottom right part of the slide, simplex interior. But if we lower the temperature of our model, the distribution will be tend to some discrete distribution on the simplex vertices, which are displayed on the left top part of the slide, simplex vertices. Mm-hmm.
So it means these two distributions does not allow to select this kind of model?
Yes, they do not allow to select this kind of model. For this kind of model, we need to use some different distributions, and they are, in my opinion, more simple. For example, we can use something like binomial distribution for each of the vertex.
No, how come? We could assign a vertex of the Dirichlet distribution to each vertex of the cube.
Yes.
Am I right?
Yes. Yes. You're right. If we need this structure, but in practice it's often these distributions are often used for this case, for the bottom left case, when we do not need to search across all the vertices of the cube, only on the simplex of the cube, or on the simplex, sorry.
Mm-hmm. Okay, so this talk is not about the regularization path, the path of optimization procedure.
Yes.
Mm-hmm. So we cannot say we have a construction which goes through this cube, and we call it, say, set of gamma or a set of model parameters W.
I think it's out of the scope of my talk, but we can model this sequence of gammas that will go through, will build some trajectory for the optimization procedure. Yes.
Mm-hmm. How this sets will be shown in the plate notations, in your plate notations. Can we go to one of the plate notations now? And just a second, I erase this picture. Yes. So could you again explain what does this notation mean?
This notation means the following. We have some data set, which is represented by X and Y, and we have parameters and the structure. The structure can control the parameters because the structure for us is the primary object. And both of these objects, the structure and the parameters, can be controlled using some hyperparameters. We do not distinguish the hyperparameters for the structure and for W, for the parameters of the models, because they are optimized in one procedure.
Mm-hmm. So again, age. Can I hold this slide for a moment? Say we have a model.
Mm-hmm.
Oh, pardon. Just a second. I would like to draw. F is color is equal to gamma 1, W1, X1 plus gamma 2, gamma 2, W2, X2 plus epsilon.
Mm-hmm.
So W1 and W2 are here.
Yes.
Okay, this vector is this matrix. Then we have an error. We denote this error L or S.
It's L.
L.
Mm-hmm.
Great. So L is F minus Y, and this since this is vectors, then we put here a quadratic form, transpose F minus Y plus W, this W minus W. No, I put here 0. Just a second. 0 A transpose W minus 0, and these two matrices, covariance of the error epsilon and covariance of parameters, are what? Are H.
Yes,
Am I right?
Yes, you're right.
Okay, that is great. Vectorize A, comma B, like that. And where is the we have how many random variables? We have epsilon, W, and gamma.
Yes.
Epsilon say normally distributed, W exactly normally distributed, gamma Dirichlet distributed. And where are the parameters from the Dirichlet distribution?
These parameters can be hyperparameters. For example, the Dirichlet distribution can be also presented with two parameters, concentration and temperature, like Gumbel softmax. It can be parameterized in this way. And so the concentration will be in the hyperparameters, and the temperature will be in the metaparameters.
Okay, and these are concentration, say C and T, right?
Yes.
Are here in the vector H.
Mm-hmm.
So the vector H controls random variable gamma and random variable W. Okay, it fits.
Mm-hmm.
These two vectors controls the target variable Y, and also we have non-random independent variables X.
Yes.
Fine, but what we missed? We missed these two halves, first and second, which we inherit from the statistic inference.
Mm-hmm.
So we denoted lambda 1 and lambda 2. So, and these two lambdas are metaparameters, right? Where are they here?
They are
Meta
here where you wrote it.
Parameters. No, in this picture, lambda.
They are not on the plate notation because they control the hyperparameters and they are assigned expertly, not during the optimization. But if we continue to draw the plate notation, it should be some lambda that has an edge to the h to the hyperparameters.
So you propose to insert lambda here. Lambda controls. Okay, it's not so easy. And in the second plate notation, could we find this lambda?
So I'll try to find it. Second plate notation.
Where is it?
Yes. No, this is an extension of our plate notation with some with an extension that the A matrix controls the W and the S concentration controls the gamma. Both of these vertices are each the hyperparameters.
Okay. So let us speculate on could we put a regularization pass? So the pass, the set of points we have during the optimization, during a optimization procedure into this diagram. So during the optimization procedure, the model parameters change, the model structure change, and probably hyperparameters change or not. Or we consider the model parameters are the same during the hyperparameters are the same during the optimization procedure.
No, the hyperparameters can also vary during the optimization procedure if we, of course, vary the meta parameters. So yes, they control the hyperparameters. Therefore, the hyperparameters can also be different for the regularization path.
Or shall we just put all this construction in brackets and lower input, put lower index, say K is a step of optimization procedure, or if the optimization goes smoothly, so let it be not K, say tau or what?
Yes, I understand the idea, and yes, we can do this. Of course, this procedure will vary the hyperparameters, the parameter, and the structure. So this plate notation is basically for one value of meta parameters, and we can replicate it for all the steps of our optimization.
Okay. Yes, definitely. We have to draw, first of all, this kind of picture. We have several parameters, say W1 and W2. And here we have lambda. And changing lambda, we change values of parameters and values of hyperparameters, like that. Here we have increase in the hyperparameters. Here we have, say, decrease. And this will be called regularization path or optimization path. Optimization path. Okay, dear friends, any comments on this work? Anatoly, if you hear me, I'm sorry I missed the schedule and we started, say, about 5 minutes ahead of the schedule. But
Hi, Vadim.
anyway,
no, unfortunately, I'm really not, how to say, I cannot say much neither about neural nets nor about Bayesian optimization. Sorry, it's
no problem. In fact, we are speculating on this stuff. We have a vector W to optimize, and we invent ways to analyze the change in this vector, and we call it the regularization path. And say we have a space of parameters, and these paths we obtain during the optimization procedure, and we are dreaming how to replace the optimization procedure, say Adam optimization procedure or Newton, replace these kind of procedures for neural network or for any model. So, and to do this, we have to approximate this path, this change in parameters.
Vadim, I think that you may discuss with Volodya Spokojny, who is now right into such things.
Okay.
My problem is that, you know, I understand something about model selection and stuff like this, but in the convex case, in the simple situation when, okay, you have separations and sets are convex and stuff like this. So I cannot say much about your things are very complicated from my point of view.
In fact, even not scientific, since Oleg has a slide with adversarial attack. Oleg, can you show this slide about the I clear all drawings? Yes, about the adversarial attacks. What it is? Say in the picture we just keep half of face hidden, or just draw some picture on the face, and in the parameter space, say here we have error function and the only parameters, and it looks like that. And if we invent a strategy which change this optimum to that optimum for no reason, we don't know how, we call it the robustness to adversarial attack. Of course, we cannot analyze it strictly, and most likely it is not looks like a scientific method.
You mean when you mean adversarial attack, the attacker also optimizes his strategy, or it's just
no? Attacker just put a disturbance to data.
But how the disturbance is computed? Is it kind of maximal, the worst case, or just
no? It's
from the
disturbances into measurements. Like we could put a pointer into car's camera, and the car's images will ruin the car's route, like that. Or a camera cannot recognize a person versus, say, a tree.
Because the only way I know how to deal with worst case disturbances is just to control the norm of your operator.
Yes.
I mean, so.
Yes, again, keep it as simple as possible.
Okay, so that was the end of the talk, or there will be something?
Yes, it is the end of the talk, I think.
Okay, then.
So maybe we have a break till.
Good.
Yes.
10:30, right?
Okay, we'll have a break. Oleg, thank you very much.
Thank you very much, Oleg. Thank you.
So see you 10:30.
so maybe we should start.
Dear friends, now it is 9:30 Central Time, 10:30 Moscow time. And we go after our schedule. And according to this schedule, now it's talk by Olga Grebenkova, hypernetworks to control the complexity of deep learning models. Olga is a BS Bachelor 4 student, just finished.
Hello?
Yes.
Yes. Can you give?
Please go on.
Can you hear me and see my screen?
Excellent. Yes.
Okay, so good day, everyone. My name is Grebenkova Olga, and I'm delighted to be here today to present you the work hypernetworks to control the complexity of deep learning models. This is a joint work with Oleg Bakhteev and Vadim Strijov. If you have any questions you'd like to ask, please leave them until the end when I try to do my best to answer them. Okay, the work researched the problem of deep learning model selection. Optimal model construction is the fundamental problem of deep learning, since this family of models has an excessive number of parameters implicitly. Since the problem of deep learning model selection and optimization is computationally expensive, we propose to consider not a distinct model for optimization, but a family of models that can be parameterized with a desired model of complexity parameter. We propose to represent the parameters of the model in the form of hypernetwork. Hypernetwork is a function that defines the parameters of the optimized model. The hypernetwork input is information about the structure of the desired model. The output is a vector of parameters. To control the complexity, we consider the problem of hypernetwork parameters optimization. This model generates model of a given complexity with lower computational costs in comparison with the process of direct model optimization. The resulting hypernetworks can generate both simple and complex models depending on the required model properties. An example of the resulting accuracy surface you can see on the slide. This surface can be obtained with models with different complexity. Here we can see that significant complexity regularization implies models with lower accuracy and higher robustness under pruning. So we can see that the complex model, so model with sufficient complexity, has better accuracy score, but it's not really robust to the pruning of the parameters. At the same time, models with sufficient regularization have not high accuracy at the beginning, but these models robust to the deleting of parameters. Let's move to the problem statement. There are a given data set, model, a prior distribution of the parameter vector and the RN, and a variational distribution, which is approximating a known posterior distribution. We define the logarithmic likelihood function for the model and the corresponding vector of parameters. The optimal values of the parameters can be found by maximizing of the logarithm of the model of evidence. This is the Bayesian approach to the problem. Since this integral is intractable, we will consider variational approach to solve the problem. We will estimate the integral. After estimation, we have such an equation. The first term in equation is the difference between a posterior and prior distribution of parameters, which sets the complexity of the parameter distribution with respect to a prior assumption. It is determined by the Kullback-Leibler divergence. This term can be interpreted as regularizer that controls the divergence between prior and variational distribution, and thus can be interpreted as a complexity regularization term. The second term in this formula is the expectation of the likelihood. We consider the problem of model parameters optimization by the generalized evidence function. It can be defined in different ways. In this work, we consider three variants where the complexity parameter lambda controls the influence of the prior distribution on the choice of the final model. In the work, we prove the theorem which establishes a relation between the formulas presented on the slide. The first and the second statements from the theorem establish the relationship between first two optimization function based on probabilistic assumptions and non-probabilistic optimization function with L2 regularization, which is the third this on the slide. This relationship established for the case when the vector alpha corresponding to the variational covariance is sufficiently small. The third and the last statement from the theorem shows that the first expression, so this one, can be considered as a correct probabilistic approach for variational parameters optimization, where lambda controls the dataset size for the evidence lower bound. To sum up, first two expression can be considered as a correct optimization function based on probabilistic assumptions with regularization that controls the importance of prior distribution. But only the first expression gives us opportunity to control the prior importance straightforwardly using the parameter lambda. For every variant of generalized evidence function, we can set an optimization task. We want to find such a mapping from the set of possible complexity parameters to the set of models parameters, so that for an arbitrary value of the complexity parameter lambda, for every lambda, it would give the maximum to the following function. In order to solve this task, we propose to use the hypernetworks. What is the hypernetwork? Hypernetwork is a parametric mapping from the set lambda to the set of model parameters. In our work, we use the following linear mapping, where B2 and B3 are the parameters not depending on lambda. A natural extension of such mapping is the piecewise linear mapping, which also was implemented in this work. The parameters of each model can be pruned after optimization using the approach described in the paper of Alex Graves. And as a criterion for removing the parameters, we use the relative density of the model. We also consider the simplified criterion, which can be applied without probabilistic assumption. It is on the slide 2. The proposed method is based on the assumption that hypernetwork approximating models optimized with different values for the complexity parameter, for the complexity lambda, approximate them not only in terms of performance, but also in statistical properties. This allows us to obtain models from hypernetworks, tune them, and prune their parameters in similar way to usual models. And in the work, we prove the theorem that confirms this assumption in the simple case of compact domain containing the minimum of the model for all complexity values. So theorem on the slide. In order to analyze properties of the generalized evidence function and the proposed method of implementation of hypernetwork, we carried out in experiments based on the MNIST dataset of handwritten digits and the CFR10 dataset of tiny images. We compare following implementations of neural networks of variational, reparameterized network, and Bayes neural network. They correspond to different general evidence function. And furthermore, we compare same networks, but with linear and piecewise linear hypernetwork. For all experiments, we use Vadim optimize with learning rate, which is on the slide. We train models for 50 epochs, and so mini batch size is set to 256. A logarithm of the variance for the variational distribution and its signalization as a logarithm, we use -3, and as the prior variance, we use 1.0. For neural net, we use for experiments on the MNIST data set, we use next neural network consisting of two layers, 50 and 10 nearest correspondingly, where the second layer contains the softmax function. As the quality criterion, we choose accuracy. On this slide, you can see the results of the experiments for the MNIST data set. So there are the dependence graphs for accuracy on the percentage of the deleted parameters. And as you can see for the first graph, variational method allows us to delete approximately 60% of parameters without significant loss of classification accuracy for almost all lambdas except value 100. For value 100, we can delete approximately 80% of the parameters. On the figure B and C, we can see reparameterization net and the base net correspondingly. As we can see, the classification accuracy hardly changed, but for the models with variational approach, so variational and reparameterization net, we can say that these models are more robust for the deletion of the parameters. In the second line, we can see the same models, but with linear hypernetwork. As we can see, for all lambdas, the classification accuracy has improved. The deviation from the mean also increased for the sufficient percents of the deleted parameters. Furthermore, the models become more stable, so the classification accuracy less depends on the removal of the parameters. In the last row, we can see the models, but with the piecewise linear hypernetwork. These models with this implementation of hypernetwork showed similar behavior to models that were trained directly during pruning. Moreover, for all values of lambda, more stable models were obtained. The same experiment was carried out for the CFR10 dataset. The results is on the slide. We have the same great results. Variational methods allows us to delete approximately 60% of the parameters in contrast to the BaseNet, where we can delete only 40% of our parameters. And the second row, you can see models with linear hypernetwork. And as we can see, the models become more robust. And in the third line, we can see the models with piecewise linear hypernetwork. And these models approximate the behavior of direct models more precisely than linear hypernetwork. And for both realizations of implementations of hypernetwork, we can see that models are more robust. So what is their conclusions of our experiments? We gained all the results from experiments in one graph. So we averaged results for every lambda. For among all lambdas. And as we can see, for both experiments, the variational net are one of the most robust models and with one of the best accuracy. Furthermore, hypernetworks approximate the direct models are really good. So as you can see, for example, so orange is the BaseNet, in the red is the BaseNet that was obtained from piecewise linear hypernetwork. And as we can see, the behavior of them is the same. So, and for the CFR dataset, we have the same behavior, so the same results. So what's conclusions? We investigate three forms of regularization. We have experimentally and theoretically proven that models obtained using hypernetworks retain similar properties during pruning, for example, accuracy. This was proved for different models and for different data sets. And in future, we're going to research other variants, so implementations of hypernetwork and advanced methods, so other methods of controlling models complexity. thank you for your attention. If you have any questions you'd like to ask, I'm ready to answer them.
Thank you, Olga. Dear friends, please ask your questions, and Olga, please go to the slide number 10. This is brilliant collection. And the first question is, again, the neural networks approximate some variables, right? What variable approximate the hypernetwork?
Approximate the model parameters. So we have the model parameters that we can optimize as usual. And the main idea of our method, one of the main ideas of our method, is to use hypernetwork. So it's the model that approximate these models. So that desired model, that so usual models that we want to, we usually work with the desired models.
Okay, and we have a collection of nine neural networks, and
Yes.
all of these neural networks are what? Say, when I see, just a second, when I see, do you have just hypernetwork, hypernetwork? Say number D, variational linear hypernetwork. What does it mean? It means you have hypernetwork and the network
the variational neural network. So we have three main networks, as we can say, with that corresponds to general evidence function, for example, variational representative based neural network. And then we try to approximate them with different implementations of hypernetwork. So linear, in our work, it's linear and piecewise linear hypernetwork.
Again, what function you have evidence
a
function?
general evidence function, yes. So this is, so we have different, we can define them in different ways. In our work, we decide that
it is our quality criterion, the target function we optimize.
Optimization function, yes.
Okay, please go back and continue. Since my question, in fact, was what is the difference between these bunch of models, between this set of models? Please go into details.
Okay, so we have different for the is it clear that for the first three models we have different optimization function? This is the difference between them.
Yes, and just a basic optimization algorithm runs to get the optimal parameters for this model.
Yes,
excellent.
What they
it's clear. The first three.
Next, yes. For
the next three.
For the three next. So D, E, F models, we have a linear hypernetwork that generates the weights for these, so for variational representative network or base network. So we use optimization function that we use general evidence function, different general evidence function, and implementation of linear hypernetwork.
And we get rid of the optimization algorithm completely, or not?
Not. We use, we optimize not the models directly, but we optimize the hypernetwork. And that's why, so yes, we have the optimization algorithm, but not for the model itself, but for the hypernetwork that will generate the weights for this model later. No, not later, but...
Okay, and the last three?
The last three is another implementation of linear hypernetwork. So we can, first of all, hypernetwork is a parametric mapping, and we can use the mapping that we want, so whatever we want. And so in our work, we use linear hypernetwork and piecewise linear hypernetwork, but in fact, we can use everything. The question is the efficiency of these hypernetworks. So in our work, we compare two implementations, but maybe there are some more interesting implementations, we use them because they are simple and have good results.
And we have only one criterion to compare these 9, or what?
Not one criteria. We have accuracy, and
yes.
then we prune the parameters of the models in order to see what will happen with the accuracy after this. And as we can see, for the BaseNet, it's the model is not so robust as for the variational net, for example.
Mm-hmm.
So the accuracy, so in the CFR, for example, we can delete only 40% of the parameters, and then the accuracy is low.
Mm-hmm.
And for the variational method, we can delete 60% of the parameters, and there is nothing to worry about.
But when you say 60-80% of parameters, all the parameters number are the same, right?
Yes, it's the same structure of the models. So structure, the initial structure of the models is the same. That's why.
Okay, great. Just a second.
Okay.
Oleg, please help me.
Mm-hmm. Okay. Do you have any questions else?
May I ask a question?
Mm-hmm.
Yes.
Yeah, actually, my question was, actually, I have quite a number of questions, but just...
Oleg, Olga, sorry, extremely sorry.
There is a question.
There is a question from Anatoly.
Dear friends, do you have more questions?
Yes, Anatoly has a question.
Yeah, actually, could you explain how do you optimize? Because you say, okay, there is this function which represents regularization parameters, but now how do you optimize? How do you the optimization of the hypernetworks? What are the data you use, or how does it work? Because I did not understand.
Okay, so I understand the question. Thank you for it. We have we don't use another data for the hypernetwork, so they use MINI's data set. And in fact, hypernetwork is the usual neural network, but it produces the weights for the net that in future will classificate mixed. And in fact, so there is a two-level, not two-level optimization. So it's algorithm where when we optimize the network, that will ask the hypernetwork what is the parameter I should use. So it's the usual optimization. So it's no difference between the optimization of neural network and the hypernetwork. It's the usual neural network, but it's a result. In the result, it gives model parameters. It's not clear, I think. Yes. Okay.
And I have another question, just a small question. So, because typically in statistical models, so you say that, okay, this is something which is, okay, this is surprising for me that the notion of complexity and number of parameters is rather different for neural nets, but in usual statistical model, you expect the degradation of the quality when you remove and you prove parameters. Okay,
yes.
so, and here what you say that the model is more robust if when you remove the parameters, its performance does not change. It means that basically you can remove all these parameters and use the smaller network and it will be fine, right?
Yes, but not all the parameters, as we can see all of our models after 60 or 80% of the parameters, so the accuracy lost significantly. So, and that means that the complexity of the model has decreased. So, for example, so that these models, that parameters of these models can be the zero, and if we delete them, nothing change. Yes, and it's good that we have for this robustness.
Okay, so in fact these parameters are zero. So you
Yes,
can,
for example,
you
yes,
can safely remove them, and actually
and
now you
there's
have
no-
the smaller model. Okay, thank you. Thank you.
Okay, dear friends, thank you very much. No more questions. Then, Olga, thank you for the nice talk. And our next speaker is Maria Gorpinich. Maria.
Can you hear me well?
Yes. Yes, please share your screen. Maria is third-year bachelor student and just finished the first semester in our department, Intelligent Systems, wrote her first paper, and welcome to present.
Good morning.
Maria.
My name is Gorpinich Maria. I am the third-year student at MIPT. Today, I will report you on optimizing regularization path in knowledge distillation. This is a joint work with Oleg Bakhteev and Vadim Strijov. We investigate the problem of match-parameter selection, which is computationally expensive. The purpose of this work is to propose a match-parameter optimization method using knowledge distillation. To solve this problem, we formulate a two-level optimization problem, which is solved by gradient-based methods. To accelerate match-parameter optimization, we use prediction with linear models. Metaparameters are the parameters of knowledge distillation approximation optimization problem, namely the coefficients before terms in a loss function and the temperature. The loss function is a sum of the likelihoods of the initial dataset and the one of the distillation dataset. Temperature is a factor of logits of models in softmax function. Knowledge distillation is a model parameter optimization problem that takes into account not only information contained in the initial dataset, but also the information contained in the cumbersome model. The cumbersome model that has a more complicated structure, complex structure is analyzed. It is trained using the initial dataset. The model of the simpler structure is optimized by transferring the knowledge of the cumbersome model to a simpler model called the student model. This work is based on the article of Geoffrey Hinton. We also used the greedy gradient-based approach proposed by Елена Luketina and algorithm analysis performed in the article of Oleg Bakhteev. We state the following problem. There is given a dataset for K classification problem. We split it on the train part and the validation part. Train part is used for model parameter optimization and the validation part for meta-parameter optimization. F is a fixed cumbersome model and G is a student model. Accuracy is used as an external criterion. Define the regularization path as a sequence of parameters that are updated during optimization. The de-distillation of a student model is a student model parameter optimization with a regularization path which minimizes the results of applying the function d to the vector of parameters with the increasing number of iterations. The following loss functions are used. The train loss is a sum of the likelihood of the initial dataset and the one of the distillation dataset. The first term is multiplied by the lambda1 factor, and the second is multiplied by a lambda2 factor. There is also used a temperature factor that has the following properties. When it tends to 0, we obtain a vector that has one class with unit probability. When it tends to infinity, we obtain the classes with equal probabilities. We also use the validation loss, which is the initial loss term. Define the multi-parameter set as a vector lambda. The first two components are factors lambda1 and lambda2. The third component is the temperature. Formulate the two-level optimization problem. On the first level, we minimize L-train function and optimize model parameters. On the second level, we maximize L-val function and optimize match parameters. We can show that the following KL divergence is a special case of de-distillation. When lambda1 is equal to 0, there is only the distillation term in L-train. Also, we have a condition that must be satisfied. Using the following inequality, and that KL divergence is greater than 0, we get that condition is satisfied, and the KL divergence is a special case of de-distillation. Define the optimization operator as an algorithm U of parameter vector selection using the parameters on the next step. We optimize the parameters using eta optimization steps. Optimization algorithm has the following steps. For every step, we solve the two-level optimization problem. Then we obtain the updated value, then let lambda be equal to its updated value. Now the optimization problem can be redefined using the definition of operator U and solved with the gradient descent operator. Update match parameters successively according to the following rule. Gradient-based optimization is computationally expensive. It is proposed to approximate the multi-parameter regularization path. The path is predicted with linear models that are trained periodically after a certain number of iterations. We optimize the parameter C using least squares method, periodically with a predefined period. The period is tuned during cross-validation procedure. We test the following hypothesis on the approximation of gradient optimization regularization path with the locally linear models. We conducted the computational experiment, which purpose is to test the performance of the proposed distillation method and to analyze the resulting models and their match parameters. The method is evaluated using the Seyfarth dataset and the synthetic dataset. For the evaluation of the method, we conducted a computational experiment using a synthetic dataset. The first two features are generated from the standard normal distribution. The third one indicates that the first two features are greater than 0. We also define the labels on every object which are noisy. The size of the student model dataset is much smaller than the size of the cumbersome model dataset. Firstly, we tuned the optimization procedure. There were conducted series of experiments to determine the best epoch size and the best periods between linear model training. The first figure plots the model accuracy for different epoch sizes. According to this plot, the epoch size was chosen to be equal to 100. The figure on the right plots the model accuracy for different periods between linear models training. The best results were obtained for periods equal to 2. The student model was trained with several methods, using distillation and optimization match parameters with gradient-based methods, distillation with regularization path prediction, distillation with random match parameters. These figures plot match parameters that are updated on every iteration. We see that the optimized match parameters performed better. However, prediction using small number of epochs in the periods is very close. Also, the difference between optimized and predicted meta parameters increases with the increase of the numbers of epochs in the period. This figure plots model accuracy for different methods. The best results were obtained with the optimized match parameters. However, the results obtained after usage of linear models are only slightly worse compared to the previous ones. Also, the difference of model accuracy for those methods becomes lower with the increasing number of iterations. Also, the proposed method was evaluated on 10% of CIFAR-10 dataset of 60,000 color images, 32 times 32 pixels in 10 mutually exclusive classes. Each class contains 6,000 images. Dataset is divided into the train part and the test part. In our case, the train part contains 5,000 images, and the test part contains 1,000 images, which is 100 images of each class. We used accuracy as an external criterion. We compared the student model performance without distillation after 5 restarts and with the distillation over SNET and of CNN after 20 restarts. The value of the lambda1 ranges from 0 to 1, and the temperature ranges from 0.1 to 10. The first figure plots model accuracy depending on the value of lambda1. Different dots denote the accuracy of the model without distillation and with distillation over SNET. As we can see from the plot, the accuracy is lower when lambda1 is equal to 0. The next figure plots the accuracy depending on the temperature. It shows that the accuracy is lower when the temperature algorithm is equal to 0 or it's close to -1 or 1. The last figure plots the accuracy depending on the temperature and lambda1. The accuracy is shown with color. Here we can see that the accuracy obtained without distillation is lower than the one with distillation. Then a convolutional neural network with 3 convolutional layers and 2 fully connected layers was used as the composite model. These figures plot metaparameters that are updated on every iteration. We can see that the values of predicted metaparameters are close to the optimized ones. This figure plots student model accuracy for training without distillation, for training using distillation and random metaparameters, distillation with simultaneous metaparameter optimization, and distillation with metaparameter prediction. As we can see from the plots, the model accuracy of training using distillation is much higher than without it. We obtain the best accuracy if metaparameters are optimized. As we can see from the experiments, the model accuracy obtained after usage of our method is only slightly lower than the one after usage of optimized metaparameters. However, this method is less computationally expensive compared to the usage of only gradient optimization. The parameter optimization problem for deep learning models was analyzed. The generalization of knowledge distillation method was proposed that uses gradient-based metaparameter optimization. Model parameters are optimized on the first level and metaparameters on the second. Model parameters, the properties of the optimization problem and methods to predict the metaparameter regularization path were analyzed. The proposed generalization produces models with better performance characteristics using less number of iterations. The combination of these approaches was evaluated in the numerical experiment on a CIFAR-10 dataset and on the synthetic dataset. The computational experiment showed the effectiveness of gradient-based optimization for the selection of metaparameters of the distillation loss function. The possibility of regularization path approximation using linear models was analyzed. In future, the further investigation and the analysis of the quality of metaparameter regularization path approximation with more complex predictive models is planned. That's all. If you have any questions, you may ask them.
Yes, please.
May I?
Yes.
Actually, how do you measure the accuracy for 10 classes in this example? What is the accuracy?
It is the sum of the correct labels divided by the number of objects and
okay, sorry, this is a precise hit.
Mm-hmm.
Okay. And I have another question, actually. Why the student network is much simpler than the professor network?
It has a simpler structure. It has not so many nodes in layers. Yes, it has not so many nodes in layers. It is correct for the experiments on the CIFAR-10 dataset and for the one on the synthetic dataset.
But if instead of this, we would use the structure, which is similar to the structure of the professor, but okay, it has less data and still it has this distillation thing.
Yes, and it is important that we use student network that has a simple structure, but it is not very different from the structure of a campus model.
Okay, thank you. Thank you.
In fact, I continue Maria's answer, and I could answer that because of the problem statement. The problem is to reduce the dimensionality of the parameter space, and we just set simpler student and select a student among the set of students using the professor network. That's all. That is a requirement for the simplicity. So professor lives in the high dimensional space and student lives in low dimensional space. and we are solving the dimensionality reduction problem. Maria, could you go to the slide with temperature and parameter plot with diamonds and crosses? Yes. No, the next. No, the square where the x-axis is temperature. Yes, yes. Log t lambda 1. Right. Could you explain this plot in details? What we should see on this plot?
Okay, on this plot we have the accuracy depending on the parameters lambda 1 and temperature factor. And in this experiment, we don't use lambda 2 explicitly because it is equal to 1 minus lambda 1. So there are also two match parameters. And on the first plot, we see that when the value of lambda 1 increases, the accuracy is higher, and when it is almost equal to 0, it becomes lower. And we also see that the performance of the network which trained without distillation is I can say maybe significantly lower than the performance of the network which uses distillation. On the second plot, we see that it is also true. The network performance with distillation is higher than without distillation. And we can also see that when the logarithm is not too small and is not too low and not too high, the accuracy is the best. Maybe if you maybe when logarithm is equal to 0.5, we can see that it has the best results. And on the third plot, we can see the graph where we plotted the accuracy and showed it by color. It depends. It is depending on lambda 1 and the temperature logarithm. We also see that without distillation we obtain lower accuracy, and with distillation we obtain higher accuracy. And we see that the higher accuracy is when the logarithm is also close to 0.5, and lambda 1 is greater than 0.6.
Yes. Please recall, the lambda 1 is the more lambda 1, the more we trust in teacher or in student? Go to the formula.
The more lambda 1, the more we trust in teacher.
In teacher, okay. The more lambda 1, the bigger lambda 1, the more we trust in teacher. And yes. And t, the bigger t, the more complex who, a student or teacher?
If t is bigger,
yes,
then we distill more information from the CAMS model. So
what we shall conclude from these three plots? We must more trust in teacher and gain more information from teacher than from data.
I think the temperature is not for trusting to teacher. It's something else.
No.
It's not trusting.
It's lambda. Yes.
Yes. It's not for trusting, yes.
Okay, so I think that we should
just return to
we should use the
slide
weighted
5,
sum because
by definition of temperature. Can we return to
Maria, Andrei, please let Maria answer.
return to what slide?
5, 6, where temperature is defined. I think it'd be more easy. Oh, yes, here, 6 slide, 6.
Yes.
In loss function, temperature T. It just smooths prediction of teacher and student.
Yes.
Just smoothing.
Okay, and what these plots tell us?
These plots tell us that the performance of the model with distillation is better than without distillation.
Okay, great.
This was a
yes.
like baseline experiment, but on this Seifert and dataset, yes.
Okay. Yeah. Yes. Okay. Of course, it depends on data on the problem itself. If, dear friends, if there is no questions more, then Maria, thank you for the nice talk. And
okay. Thank you.
The next speaker is Mark Potanin. But in this case, I need your help since, unfortunately, Mark Potanin couldn't take part in our seminar, in our workshop, but he left a record of his talk. If you're not against, I will try to play this record. Just a second. And I'm not sure if you will hear the sound. So I will hit the button run, and you please immediately tell me, is the sound good or not? If the sound is not good to be listened to, we just skip this talk and go to the next talk. Go to the next talk. So first of all, I shared the screen, right?
Yeah.
Okay, and I will play the sound.
We doesn't hear.
No.
I think you just need to press share. In share screen, you can press share sound, and we can hear your sound.
In share screen, I must press share.
In button of the button of the window.
Yes.
Share sound. Sorry. I stopped share.
Who can share? No, there is no such option.
Share screen, and after you press share screen, on the bottom of this window, you can share sound.
Yes, of course. Thank you very much, Andrii. Pam, and
let's try
again.
Hello, dear participants of the work.
Thank you. So we will continue, and after this talk, it is just 6 minutes. I try to answer the questions. So go on.
Sure. My name is Potanin Mark. I am a PhD student at MIPT. My scientific advisor is Vadim Viktorovich Strijov. Today I present to your attention my talk on the generation and selection of agnostic models. The purpose of this work is to study a method for generating and choosing the structure of neural networks that are weakly dependent on the weight parameters. There are genetic algorithms for searching neural network topologies, for example, MIPT. They are looking for both optimal structures and weights at the same time. In turn, the VAN algorithm, which we will talk about today, is focused only on finding the architecture of the neural network. This slide provides links to related works. The first article is the main source of inspiration for the current work. In the second work, the MIPT neuroevolution algorithm is described in details. The third work uses an evolutionary algorithm to build recurrent neural networks. The goal of NASP methods is to automatically create neural networks architectures. The proposed networks after training should outperform networks that was created manually. So the weights of the neural network are the solution to the problem. The found architectures are simply the most optimal storage for the weights. In order to create architectures that encode solutions themselves, the importance of weights must be minimized. Replacing weight training with weight sampling ensures that performance is a product of the neural network topology alone. This slide shows the diagram of the VAN algorithm. We avoid weight training by choosing single shared weight. The initial population is composed of sparsely connected networks, networks with no hardened nodes, and only a fraction of the possible connections between input and output. The search for VAN can be summarized as follows. An initial population of minimal neural network topologies is created. Each network is evaluated over multiple rollouts, with a different shared weight value assigned at each rollout. Networks are ranked according to their performance and complexity. A new population is created by varying the highest ranked network topologies chosen probabilistically through tournament selection by crossbreeding and mutation. The algorithm then repeats from step 2, yielding weight-agnostic topologies of gradually increasing complexity that performs better over successive generations. Now let's talk about the stage of evolution of neural network architectures. In each generation, a new population is created based on the fitness ranking of the old population by breeding. The unfittest of the population are not allowed to take part in the breeding, whereas the fittest pass on to the new population immediately and unchanged, so-called elite. The new VAN architecture adopts the activation functions and nodes of the fitter parent, but the connections are a mixture of both parents. The resulting individual subsequently mutates in one of three ways. A connection is added, a node is added, an activation function is changed. During evaluation, the performance of each architecture of the current population is measured by feeding it with data input samples and comparing its prediction with the target samples. However, not only the performance of a network architecture matters, but also its complexity. For this reason, the fitness ranking of the different architectures is not only done according to their prediction performance, but also according to their complexity. This slide shows the fitness function formula by which we evaluate each architecture. To assess the quality of the algorithm during the experiment, the following set of metrics is used: train loss, test loss, number of connections, number of hidden layers. This slide shows VAN's metrics. I considered a regression problem on a concrete dataset. The dataset contains 1000 samples, 800 of them went to the training set and 200 to the test set. The dataset contains 8 features and 1 dependent variable. The figure shows the work of the algorithm for 200 iterations. The population size is 200 individuals. Shared is selected as the weight assignment method. That is, one weight value from the list is assigned for all connections. As you can see, the average error of the population on the test set decreases, as well as the average error of the population during training of the algorithm. The number of connections is growing, which is also a positive trend. Conclusion. A method for generating and choosing the optimal structure of the model is considered. Considered algorithm weakens the importance of training neural network weights. The experimental results confirm that the iterative algorithm leads to obtaining weight-independent neural network structures. Thank you for your attention.
Thank you, Mark, and thank you for your attention. Please ask your questions, and I try to find a way to answer. But since our workshop entitled as Maths and AI, I must say for the first part, for the part math, that the genetic algorithm is a stochastic process, of course, peculiar one with jumps, with shifts, etc. But since it is a stochastic process, what is the random variable? The random variable here is a neural network structure. These variables, which Oleg Bakhteev in his first talk, is denoted by gamma. So not only these simplest models like weight agnostic neural networks could be modeled, but any deep neural networks too. We just must set the basis, the vector gamma, which represents the model as a graph, as a random graph, as a randomly colored random graph like that, and run this process to sample the best structure to select from. Okay, friends, what can say you?
I have a small question.
Yes.
What's the practical side of the one, I mean, weight agnostic neural networks? Could you please say when it's more preferable to select the model using weight agnostic neural networks in comparison of convolution? No, I mean CNNs or MLPs, traditional neural network architectures.
The most fascinating, thanks for the question, the most fascinating practical applications of one was used by John Koza and his students Ivan Zelinka and Susanna Aplatkova about almost 20 or even 30 years ago. And this time it was called symbolic regression or genetic programming, and they constructed antennas, extremely peculiar kind of antennas to transmit a radio signal in mountains. So, and these antennas was the functions like this. In fact, it was models of antennas to construct. And here we are constructing models as neural networks. So the story is the same, but practical application is radio transmission.
Oh, okay, thank you.
Mm-hmm. Okay, friends, our next speaker is Andrii Hrabovyi. He is a master student, MS2, and Andrii, knowledge transfer and model structure alignment. Just a second, please share your screen.
1 second, please.
And we have time according to the schedule until noon sharp. So 20 minutes you have.
Yes. Okay. Hello, everyone. My name is Andrii Hrabovyi. I'm second year student of MIPT, and today I want to tell about knowledge transfer and model structure alignment. During this work, we researched the problem of reduction the number of parameters of the deep learning model by using a more complex model and use information about complex model parameters. Complex model is called teacher, and the reduced model is called student. We consider distillation problem, and we try to use Bayesian inference for this, for solving this problem. That means that we have pre-trained teacher model with fixed parameters U, and also we suggest that we have a posterior distribution of these parameters for this teacher model, and we propose a method which allows us to consider hyperparameter of prior distribution of student model, of parameters of the student models as a function of hyperparameters of teacher posterior distribution. The main challenge here not U, but omega parameter. It's student parameters, not teacher parameters. As you can see, the space of teacher parameters and the student parameter is not the same, and the function of and structure of teacher model and student model is not the same too. And the main idea, we need to first we need to alignment a teacher structure to student structure, and after that we can use this posterior distribution over this parameter like a prior distribution for student parameters. Okay, sorry. This slide shows a generalized formulation of distillation problem which proposed by Vladimir Vapnik and Jeffrey Hinton. Here we have the feature space for teacher model, for student model, the privileged feature space for teacher model, this for student model, this for teacher's model. We have a target. It can be a classification task or regression task, it doesn't matter. But privileged feature can be given not for all objects from the data set, but only for some subset of this data set. And we call space E is an index set of object for for which the privilege information is known for teacher. Okay. Next, we assume that teacher model is given, and is given and fixed. It's an optimal model, and we need to choose a student model, and these choices is made by minimizing the loss function. And this loss function depends on the teacher model. Okay, this slide shows difference between Hinton and Vapnik distillation task. First of all, Jeffrey Hinton works. It's assumed that the feature space for teacher and the student model the same, but Vapnik is not met this condition. Okay, we have two spaces of models, these teacher models and student models. Here we can see function v and z. There are some differentiable parametric function, and here we can see some parameters t is the temperature parameter. And in this work, they propose to use this loss function. The first term is a standard cross entropy loss, and the second term is a distillation term. It's a classical distillation problem statement. Okay, and we have optimization problem which need to be solved. Okay, let's move to the Bayesian distillation. Classical distillation has disadvantages. Its method doesn't use information about teacher parameters, just use teacher prediction. And we consider a special case of teacher structure. We consider only fully connected neural network, and we denote U as matrices U and vectors U as teacher parameters, and the matrix omega and vector omega as student parameters. The student model parameters optimization based on the variational inference, but for this solution we need a prior distribution of model parameters. We can use posterior distribution of teacher parameters as prior distribution for student parameters, but only if the structure of teacher and student the same. And the main challenge, as I say in the early, the parameter spaces of the teacher and the student are not the same. And that's why we need alignment. The first case, when the number of layers is the same and the size of the corresponding layer is the same, that we can just use posterior distribution of teacher parameter as prior distribution of student parameters. But if the number of layers or the sizes of the corresponding layers are not the same, then firstly we aligns these two structures. This case. Okay, consider the case where the number of layers is the same for teacher and for student, but we have some difference in some of hidden layers. consider the map, the phi mapping, which removes one neuron from this layer, and we called vector v is a parameter. It's a result of this mapping, and the deleted parameters are denoted by v hat. This slide presents a theorem which shows that if before deleting the vector of model parameter u is normally distributed and the number of layers the same, and students have less or equal number of neurons before deleting, then the posterior distribution after deleting is the normal distribution too. It was the first case when number of layers the same, but we have a difference in the number of neurons in each hidden layers. The second case, this case when the number of layers is different. Consider the psi mapping. This map deletes one Th layer, and next theorem shows that if before deleting distribution be normally distributed, and then after deleting this distribution be normally distributed too, and in theorem we can see how a procedure for transforming the parameters of distribution before deleting to distribution after deleting. Formula here, where sigma is a parameter, mu and sigma is a parameter of normal distribution before deleting. Okay. In previous two slides, we do not specify the choice of neurons or layers to deleting. It's proposed to set some order on a set of neural network parameters. Firstly, this order we can set by using. Firstly, we can use randomly order on the set. Always we can do that, but we can use optimal brain damage method presented by Likun in 1989. Or we can use method based on posterior distribution analysis, or we can use multicollinearity analysis for set some order on the parameter and delete one by one from this order. We are considering a synthetic data. The generation process is shown on the slide. We just use a normal distribution for parameters, for features, and we generate the target as a simple linear regression with parameter beta. It's some noise. We consider the structure of teacher is three-layer fully connected neural network, but for student we consider two type of structure. The first one is a three-layer neural network, but the number of parameters in this network less than in teacher network. The second structure of student model is two-layer neural network. Okay. in this slide, we can see that likelihood of the student model with Bayesian distillation grows much faster than the likelihood of the student model without distillation. And this result repeated for first structure type and for second structure type of student model. For numerical analysis, we propose to use the area difference between two graphs. For example, consider area difference between blue and red graphs. A positive area indicates that the blue model, it's mean distilled student, is better than the red model. It's a student without distillation. And the last table shows that distillation improve the area difference metrics for students with distillation compared to the students without distillation. This method works, and we can align structure of complex teacher to simpler student. Thank you for your attention. If you have any question, please, I can answer.
Thank you, Andrii, for nice talk and good timing. And dear friends, your questions.
May I ask a question?
Yes, sure.
So I was wondering about the Vadim frameworks for distillation. You said that the feature space were not necessarily the same. Like there was a privilege on a non-privileged space. So first, what is the motivation for this? And can you reproduce this feature in your framework?
Okay. For example, when you have some additional information during the training, but you don't have some information about data during the inference. For example, now I can replay some example from original article Vladimir Vapnik, article of Vladimir Vapnik. He present example of, for example, we can during the training we can use some information, future information. For example, we try to predict the result of some surgery operation. During the training, we have information about all period of rehabilitation of some people or a result of operation, and many other information which be available only after the operation, some surgery. And this information we can use as a privilege features during the training teacher. But when we distill teacher to student, we want to use student without any additional information, just information which we have before surgery operation. That's why we don't have any additional information about future and what happened after operation. I hope I try to answer for.
Yeah. Okay, but so why would you use this information in the teacher training in the first place?
Yes. So sorry.
No, please go on.
It's because it's one of the methods to use some privileged information for student. It's not Yes, I agree that it's not a part of distillation, it's a privileged learning, but we can use distillation as a some solver for privileged learning task. It's for this reason.
Okay, thank you. And can you do this in your Bayesian framework? Or maybe I missed this, but like this distinction between privileged and unprivileged features?
No, I don't compare this to. I don't compare this.
Thank you.
Yes, in fact, Andrii has excellent software of his own and framework to make a computational experiment. And if you or someone wants to take part in this kind of experiments, you're most welcome.
Yeah, thank you. No, it's just like out of curiosity. I'm just curious about. Sorry.
Okay.
Yeah.
Mm-hmm.
Do you know why the name brain damage function there for? Yeah.
Sorry, can you repeat? I don't.
No, why the name brain damage method here?
I just list a number of works which can be used for order for set some order on the parameters, neural network parameters. Brain damage, optimal brain damage allow us to set order from less relevant parameters to more relevant parameters in neural network. And here in this slide, this mapping don't choose worst parameter for deleting. They just this map say you give me a worst parameter, I will delete it, and and this theorem shows that after deleting we have the same distribution. No, we have normal distribution too, but not. But we need give worst parameter, and how to get this worst parameter is optimal brain damage. Say.
Thank you. Okay. Thank you.
Optimal brain damage is only one of method which can be used for this task.
In fact, to be precise, here is not optimal brain damage. It is most simple Bellsley method, which precedes these two methods, optimal brain damage and optimal brain surgery. Bellsley was in, say, early 18th, like that.
1989.
Oh. Oh, great. Could you show the last slide, please? I must stress the dimensionality reduction. Here we have number of parameters, line number 3. And teacher has 6,000 parameters. Student has 200 parameters. So we drop the dimensionality
more than 30 times.
30 times, yes. And what about the accuracy? Accuracy, I guess, is the same, right?
Probably the same, but I don't show that on this graph. I just compare different students. I compare a model with the same parameter, with the same parameter space.
Yes.
But for some students, I use information about teacher parameter for 4 and 5 columns, but for third column, I don't use information about teacher parameters. I compare only student. I don't compare student with teacher. Unfortunately.
I guess usually, since the error is the same, the variance of the error is the same, or the student has lesser variance, but we just have 30 times drop in the dimensionality.
Yeah.
Mm-hmm.
It's my idea to reduce
Yes.
the number of parameters.
Yes. Anatoly just asked Maria Gorpinich a question about why student model is must be simpler than the teacher.
It must be simpler because it's less because if model simpler, that their variance in their prediction is less after training. For example, we train one model, second model, third model, fourth model, and many models train. If model simpler, that this model be more similar after training, because number of local minimum during optimization task be
lesser.
Less local minimum during optimization.
Okay. So, friends, now it's 12 o'clock sharp. What?
No, I had a last question, or you want to
yes,
end
yes.
this? Okay,
yes.
Welcome.
Just out of curiosity, we talked about adversarial examples this morning, and just does the fact that you're distilling your networks improve the robustness of the resulting model? Like, it's just out of curiosity, can the student be more robust than the teacher because it has less parameters on these? Yeah.
Yes, it can be. And even in this experiment, student be more accurate than teacher. Even it's bad that I don't show it in this slide, but if we add a graph of a teacher in this graph, we can see that a student on the first graph more accurate than teacher. Well, likely more accurate than teacher. Yeah. A little bit, but accurate, but more accurate.
Say, in theory, we easily can show pro and contra variance. In practice, we pray yes, and the experience show yes.
Okay, thank you.
Thank you.
Thank you. So we went for the next session, which will start when? Anatoly, could you help me, please?
So it will be 2 p.m. Yeah.
2 p.m. exactly.
Time, yeah.
Great. So in 2 hours, we'll meet here. Thank you very much.
Okay, thank you. Thank you very much, Vadim.
Thank you, Anatoly.